Let's continue about learning mass spectrometry. Detection, a part called detection. A detector counts the number of ions at different deflections. The data is plotted as a graph or spectrum of different masses. Detectors work by recording the induced charge or current caused by an ion striking a surface or passing by. Detectors work by recording the induced charge or current caused by an ion striking a surface or passing by. Because the signal is very small, an electron multiplier, Faraday cup, or ion to photon detector may be used. Detectors work by recording the induced charge or current caused by an ion striking a surface or passing by. Because the signal is very small, an electron multiplier, Faraday cup, or ion to photon detector may be used. The signal is greatly amplified to produce a spectrum. Mass spectrometry uses. Mass spectrometry is used for both quantitative and qualitative chemical analysis. It may be used to identify the elements and isotopes of a sample to determine the masses of molecules and as a tool to determine and help identify chemical structures. It can measure sample purity and molar mass. Mass spectrometry, MS instrumentation. Sample is there, gas sample injection point, and then sample vaporization happening in the sample vaporizer, heater, electron beam is applied, and then accelerated ions are just passed into the magnetic field, and later the detector detects them. NMR spectroscopy. Nuclear magnetic resonance spectroscopy is the study of molecules by recording the interaction of radio frequency RF electromagnetic radiations within the nuclei of molecules placed in a strong magnetic field. NMR spectroscopy is a spectroscopy. Nuclear magnetic resonance spectroscopy is the study of molecules by recording the interaction of radio frequency electromagnetic radiations with the nuclei of molecules placed in a strong magnetic field. NMR spectroscopy is a spectroscopy technique based on the nuclear magnetic resonance of atoms of the sample being examined. The sample is placed in a magnetic field and the NMR signal is produced by excitation of the nuclei sample with radio waves into nuclear magnetic resonances, which is detected with sensitive radio receivers. The intramolecular magnetic field around an atom in a molecule changes the resonance frequency, thus giving access to details of the electronic structure of a molecule and its individual functional groups. The intramolecular magnetic field around an atom in a molecule changes the resonance frequency, thus giving access to details of the electronic structure of a molecule and its individual functional groups. Next principle. It is based on the fact that the nuclei of most of the atoms show spin and all nuclei are electrically charged. It is based on the fact that nuclei of most of the atoms show spin and all nuclei are electrically charged. NMR spectroscopy is based on the absorption of electromagnetic radiation in the radio frequency region, and nuclei of atoms have spin and electrical charge, so they generate magnetic fields. Nuclei of atoms have spin and electrical charge, so they generate magnetic fields. In the presence of an external magnetic field, nuclei of atoms align themselves either in the direction of the external magnetic field or in the opposite direction of the external magnetic field. It is based on the fact that nuclei of most of the atoms show spin and all nuclei are electrically charged. NMR spectroscopy is based on the absorption of electromagnetic radiation in the radio frequency region. Nuclei of atoms have spin and electrical charge, so they generate magnetic fields. In the presence of an external magnetic field, nuclei of atoms align themselves either in the direction of external magnetic field or in the opposite direction of the external magnetic field. And in the presence of an external magnetic field, energy transfer takes place between the ground state to the excited state. It takes place at a wavelength that matches with radio frequencies, and when the electron returns from an excited state to ground state, it emits the radio wave of the same frequency. It takes place at a wavelength that matches with radio frequencies, and when the electron returns from an excited state to ground state, it emits the radio wave of the same frequency. This emitted radio frequency gives NMR spectrum. This emitted radio frequency is proportional to the strength of the applied external magnetic field. NMR spectroscopy working. Place a sample in a magnetic field, excite the nuclei sample into nuclear magnetic resonance with the help of radio waves to produce NMR signals. These NMR signals are detected with sensitive radio receivers. The resonance frequency of an atom in a molecule is changed by the intramolecular magnetic field surrounding it. Then NMR spectroscopy instrumentation, sample holder is there. It's a glass tube. And magnetic coils. Magnetic coils generate magnetic field whenever current flows through it. Permanent magnet. And then sweep generator modifies the strength of the magnetic field which is already applied. Radio frequency transmitter reproduces a powerful but short pulse of the radio wave. Radio frequency, it helps to detecting the receiver radio frequencies. RF detector, it helps in determining unabsorbed radio frequencies. Recorder, it records the NMR signals which is received by the RF detector. Readout system, a computer that records the data. Next, applications of NMR spectroscopy. It is used for quantitative analysis of mixtures of compounds. It is used for quality control. It is used to determine the molecular structure of compounds. It is used to detect the purity of samples. It is used in food science. It is used in the study of drugs. It is used in the study of biofuels, cells, and nucleic acids. So magnet is there, magnet controller, and RF transmitter, detector, absorption, and we just print the result. Then biomolecular NMR spectroscopy. Proteins. Within the field of protein NMR spectroscopy, an important technique is structural biology. A common goal of this investigation is to obtain high-resolution three-dimensional structures of a protein. NMR spectroscopy is usually limited to proteins smaller than 35 kilodalton, although larger structures have been solved. NMR spectroscopy is often the only way to obtain high-resolution information or parallel, partially or wholly intrinsically unstructured proteins. It is now a common tool for the determination of conformation activity relationships where the structures before and after interaction with, for example, a drug candidate is compared to its known biochemical activity. NMR can also be used to obtain information on the dynamics and conformational flexibility of different regions of a protein. Nucleic acids. Nucleic acid NMR is the use of NMR spectroscopy to obtain information about the structure and dynamics of polynucleotide acids such as DNA or RNA. Nucleic acid NMR is use of NMR spectroscopy to obtain information about the structure and dynamics of polynucleotide acids such as DNA and RNA. Nucleic acids have a smaller percentage of hydrogen atoms, which are the atoms usually observed in NMR spectroscopy, and because nucleic acid double helixes are stiff and roughly linear, they do not fold back on themselves to give long-range correlations. Can be used to determine local structural features such as glycosidic bond angles, dihedral angles using the Card-Plus equation, the sugar-Pucker conformations. NMR is also useful for investigating non-standard geometrics such as bent helixes, non-Watson-Crick base pairing, and coaxial stacking. It has been especially useful in probing the structure of natural RNA oligonucleotides which tend to adopt complex conformations such as stem loops and pseudoknots. NMR is also useful for probing the binding of nucleic acid molecules to other molecules such as proteins or drugs by seeing which resonances are shifted upon binding of the other molecule. Then carbohydrates, the structures and conformation of carbohydrates in the field of drug delivery and drug discovery. Knowledge of energy minima and rotational energy barriers of small molecules in solution can be found using NMR. Looking at free ligand conformation preferences and conformational dynamics respectively. This can be used to guide drug design hypotheses since experimental and calculated values are comparable. Then the next one is ESR spectroscopy. Electron spin resonance, also known as electromagnetic resonance or electron paramagnetic resonance, is a branch of absorption spectroscopy in which radiations having frequency in the microwave region is absorbed by paramagnetic substances to induce transitions between magnetic energy levels of electrons with unpaired spins. ESR is based on the fact that atoms, ions, molecules, or molecular fragments which have an odd number of electrons exhibit characteristic magnetic properties. An electron has a spin, and due to spin, there is magnetic moment, and used for the investigation of different kinds of paramagnetic species in solid or liquid states. So, what is ESR? ESR is electron spin resonance, also known as electron magnetic resonance or electron paramagnetic resonance, is a branch of absorption spectroscopy in which radiations having frequency in the microwave region is absorbed paramagnetic substances to induce transitions between magnetic energy levels of electrons with unpaired spins. ESR is based on the fact that atoms, ions, molecules, or molecular fragments which have an odd number of electrons exhibit characteristic magnetic properties. An electron has a spin, and due to spin, there is magnetic moment. Then used for the investigation of different kinds of paramagnetic species in solid or liquid states. Principle of electron spin resonance. Principle of electron spin resonance. An electron is a charged particle. It spins around its axis and causes it to act like a tiny bar magnet. When a molecule or compound with the unpaired electron is placed in a strong magnetic field, the spin of the unpaired electron can align in two different ways, creating two spin states. The alignment can either be along the direction parallel to the electric field, which corresponds to lower energy state, about ms is equal to minus half, opposite anti-parallel to the direction of the applied electric field, ms is equal to plus half. The two alignments have different energies, and this differences in energy lifts the discrepancy of electron spin states. The energy differences is given by E plus minus E negative, H nu. An unpaired electron can move between the two energy levels by either absorbing or emitting a photon of energy. Working of electron spin resonance. Although the equation permits a large combination of frequency and magnetic field values, the great majority of EPR measurements have made with microwaves in the working of electron spin resonance. Although the equation permits a large combination of frequency and magnetic field values, the great majority of EPR measurements are made with microwaves in the 9 to 10 GHz region. EPR spectra can be generated mostly by keeping the photon frequency fixed while varying the magnetic field incident on a sample. A collection of paramagnetic centers such as free radicals is exposed to microwaves at a fixed frequency. By increasing an external magnetic field, the gap between the energy states is widened until it matches the energy of the microwaves. At this point, the unpaired electrons can move between their two spin states. Since there are typically more electrons in the lower state, due to the Maxwell-Boltzmann distribution, there is a net absorption of energy. It is this absorption that is monitored and converted into a spectrum. ESR or EPR technique is applicable to free radicals and compounds containing unpaired electrons or electrons. Electron energy levels corresponding to the unpaired electron split in presence of external magnetic field. The energy gap between the electronic states depends on the strength of the applied field. Most commonly used magnetic fields are of 0.34T and strength which corresponds to the frequencies. These transitions lie in the microwave region of electromagnetic radiation. The Zeeman effect, the splitting of electron spin state in presence of external magnetic field. ESR active species, free radicals having odd number of electrons. Some transition metal complexes and organometallic compounds containing metal ions having unpaired electrons in d orbitals, rare earths and actinides having unpaired electrons. Preparation of ESR spectrum. EPR spectrum is represented by plotting intensity correlated to absorbance versus the strength of the applied magnetic field. Absorption lines are broad and too noisy. So EPR spectra are commonly represented as derivative curves against the strength of the magnetic field. So second derivative spectra has even more resolution but less sensitivity. Instrument composition and components. Klystrons. Klystron tube acts as a source of radiation. Klystron tube, it is stabilized against temperature fluctuations by immersion in an oil bath or by forcing air cooling. The frequency of the monochromatic radiation is determined by the voltage applied to klystron. Klystron. It is stabilized against temperature fluctuations by immersion in an oil bath or by forced air cooling. The frequency of the monochromatic radiation is determined by the voltage applied to klystron. It is kept a fixed frequency by an automated control circuit and provides a power output of about 300 milliwatts. Then waveguide or wave meter. First we need a klystron. Klystron is for acting as a source of radiation. Next, waveguide or wave meter. The wave meter is put in between the oscillator and attenuator To know the frequency of microwaves produced by klystron oscillator, the wave meter is usually calibrated in frequency units instead of wavelength. Waveguide is a hollow rectangular brass tube that is used to convey the wave radiation to the sample and crystal. Attenuators. The power propagated down the waveguide may be continuously decreased by inserting a piece of resistive material into the waveguide. This piece is called a variable attenuator. It is used in varying the power of the sample from full power of klystron to one attenuated by a force of 100 or more. Isolators. It's device which minimizes vibrations and the frequency of microwaves produced by klystron oscillator. Isolators are used to prevent the reflection of microwave power pack into the radiation source. It's a strip of ferrite material which allows microwaves in one direction only. It also stabilizes the frequency of the klystron. Sample cavities. The heart of the ESR spectrometer is the resonant cavity containing the sample. Rectangular cavity and cylindrical cavity have widely been used. In most of the ESR spectrometers, dual sample cavities are generally used. This is done for simultaneous observation of a sample and a reference material. Since magnetic field interacts with the sample to cause spin resonance, the sample is placed where the intensity of magnetic field is greatest. Couplers and matching screws. The various components of the microwave assembly to be coupled together by making use of various sizes. Irises or slots of various sizes. Crystal detectors. Silicon crystal detectors, which converts the radiation in DC, has widely been used as a detector of microwave radiation. Magnet system. The resonant cavity is placed between the poles piece of electromagnet. The field should be stable and uniform over the sample volume. Stability of field is achieved by energizing the magnet with a highly regulated power supply. The ESR spectrum is recorded by slowly varying the magnetic field through the resonance condense by sweeping the current applied to the magnet by the power supply. Modulation coil. The modulation of the signal at a frequency consistent with good signal noise ratio in the crystal detector is accomplished by a small alternating variation of the magnetic field. The variation is produced by applying an AC signal to modulation coil oriented with respect is sampled in the same direction as the magnetic field. If the modulation is of low frequency, the coils can be mounted outside the cavity and even on the magnetic pole piece. Modulation coil. The modulation of a signal at a frequency consistent with good signal noise ratio in the crystal detector is accompanied by a small alternating variation of the magnetic field. The variation is produced by supplying an AC signal to modulation coil oriented with respect to a sample in the same direction as the magnetic field. If the modulator is of low frequency, the coils can be mounted outside the cavity and or even on the magnetic pole pieces. For higher modulation frequencies, modulation coils must be mounted inside the resonant cavity or cavities constructed for a non-metallic material, quartz with a tin silvered plating. Display devices. In order to observe the signal system connected with different devices can be used. Application of electron spin resonance. ESR spectroscopy is one of the main methods to study transition metal containing metalloproteins, to determine the rate of catalysis, to know about the active site geometry, to study denaturation and protein folding, in studies related to enzyme ligand interaction, in biological systems, study of free radicals, spin labels, study of inorganic compounds, reaction velocities and mechanisms, study of naturally occurring substances such as minerals with transition elements, minerals with defects like quartz, hemoglobin, petroleum, coal rubber, etc., conducting electrons. So this is the apparatus, electron spin resonance apparatus.